Well, should we get going? All right, so it's my pleasure to introduce Maria Garcia de Banda.
Oh my God, what are you going to say about me? That's
No relation. So Maria has had great success working with big companies building very innovative optimization solutions, but a lot of what she's learned along the way is it's not just about delivering something which finds the best solution quickly. There's a whole lot of other interesting challenges, and that's what she's going to talk about for us today. Thank you very much. Take it away, Maria.
Thank you. And hello, everyone, and thank you for coming here. So a little bit of motivation. So this decides not to work, of course. Well, since I'm sitting here, that's an easy one. I don't need to do anything. So a little bit of motivation. This talk is motivated by something that we all know, that the world needs better decision, and not just from our politicians, but from everyone. So as you know, a lot of complex problems, complex decision problems are needed to solve and are solved currently quite poorly. Why? Because they're solved by humans, and solved by humans with bad automated support, often express, if they have any automated support, there will be express sheets, things like that, and incredibly important problems. So this is problems that are in transport, in energy, in health, disaster management, lots of different areas that are incredibly important for us and for our lives, and they're still being solved not that well. So we all know here, optimization can help, and that's the main motivation. So optimization can help in solving these things, and particularly optimization technology is come a very long way. It has right now mature model languages, robust solvers, effective search techniques, and very good targeted modeling strategies from redundancies, redundant constraints, symmetry breaking. We now know a lot about how to solve these things well, and yet not being used outside, even though we can find really high quality solutions for a lot of different of those problems that I was talking about. So unfortunately, as I was saying, not many organizations use it, optimization technology. And you go, what? Some of you might go, of course they're being used. Yes, they're being used. I'll go, well, yes, particularly by companies that are talking to us in this group, but there's a huge amount of companies out there that are not using it, particularly in small companies. So optimization technology is used perhaps by big companies and often using older technology. So they know of the technology, say 10 years ago, or even 20 years ago, and they're not using things that are much more novel. And we want, this is the motivation for this talk, I want optimization to help more organizations, so not just the big ones, but many more organizations to make better decisions. And it's a great opportunity for people like us who are working on optimization, because finally we can do some real world impact that are helping the world in some way. But the question is, the thing is that this is really, really difficult. It's not as simple as we think. And my main question was, why? Why is this so incredibly bloody difficult? And can we do something about it? And that's the context of the talk, is why is this happening? And can we do something about it? And of course, the disclaimer. The disclaimer is that this is not a technical talk. Is a position talk based on my experiences using, and is a very particular on constraint programming technology, even though a lot of the things I think that is suitable for Optima, because a lot of the things that I'm going to talk about are actually, even though I discovered them while using CP, are actually very generic for other things. And it has benefited from the expertise of many. It is not just my thing. Many at Monash, in the optimization group, and also in the visualization group, because I collaborate a lot with them. So all these people and more are part of us, some of them in this room. And I should also put Andreas, actually. And people that have worked in many projects. So the first three projects that I have collaborated with companies: optimal plan layout, hydrogen plan allocation, fund allocation, but many others that others in this room and other in the group have worked, from water management, sports scheduling, nurse rostering, maintenance scheduling, again, and more. Area scheduling, etc. So what's the aim of this talk? The aim of this talk is to highlight areas of CP optimization, but actually, hopefully that are much more generalizable to the things that need more support. So it's like, this needs more support, this needs more support. It's not to offer solutions. I'll explain a little bit of how we are tackling, but that doesn't mean that is the best way to do it at all, or the only way to do it, or anything. So just, and I'm going to focus on 4 areas. And it says to ensure that domain experts can do what? They can trust our systems, they can use the systems, they can maintain the systems, and they can productize the systems. And those are the 4 things that I'm going to, and domain experts in particular. Okay, so those are going to be the kind of the 4 main things on my talk. So first, trust. And that is an important distinction. I'm talking about trust, not trustworthy, right? 2 different things. So I'm focusing on the domain expert's point of view. Even if the system is trustworthy, even if it's totally correct and fantastic, the user, the domain expert, might still not feel it is, and might not trust it. So how can we make sure the domain expert trusts the system? Hopefully it is trustworthy. That's the thing. But and I talk about domain experts, not just users. So I'm talking about the people who are actually going to use it to make the decisions, right? So who need to be, the system needs to be meaningful to them, and they need to trust them that they are actually making decisions that are relevant and they are correct. So in terms of trust, my experience is that important, well, our experiences is that domain experts need to, is important for them to do 3 things. First, feel like they understand the model. And I'm getting this more and more. The domain expert, they actually want to know that they understand the model, that they don't need to understand it completely, but they feel like they understand it, to have confidence in the correctness of the solutions, and to know the quality and the optimality gap. If they're not optimal, that's fine, but they want to have some kind of knowledge of how good the solution it is, right? Which is an issue for things like evolutionary, etc. Okay, so before I go a little bit further, I'm going to talk a little bit about, I talk about CP, constraint programming, but it is more than that. It's about the modeling and solving approach that we use in our group, actually. So how things start, it starts with a problem and some data. Someone comes with a problem on the data, and then we have here a modeling person who looks at it and uses a modeling language to create a model of a problem and how to formal of all that data, what to use and what needs to be formatted, right? So that decision is made, and it can be, in Minisync, in Essence, in Opal, in Ample, in whatever modeling language it's decided. And then it comes, the modeling language developers will have done some compiler, something like the Minisync compiler that takes this, but the model and a particular set of data, creating the instance, and calls some compiler and the libraries to create, well, sorry, the model also needs to say, I'm going to solve it with this particular solver, and there could be lots of different solvers, and it creates the solver readable code, usually, unfolded all the loops, etc. And then in the step 3, that solver readable code is given to a solver and a solution is produced. And that solver could be Gcode, Groovy, Cplex, it could be a SAT, it could be MIP, it could be CP, whatever kind of solver, right? Right, this is how we do it. We model, we compile, we solve. And yet, there's nothing in there that has a domain expert. Yeah, in theory, they are here somewhere, but very, very, very occluded. So how do we, they're going to understand the model if they are not even going to part of the model? You're going to need a chair. So they need to understand, and remember, they need to feel like they understand the model, right? So at the high level, it's not all the details, but most of it. So they need to have an idea. The parameters is the simple one because it's the input data that they're going to get, but also the variables, the solution at least. What are the things that are going to be in the solution? Again, input and output, that's usually quite clear to them. But the constraints, they need to know what are the main constraints. And I'm not talking about redundant constraints and symmetry breaking constraints, but really the hard constraints that are key, and things like the soft constraints that will go to the objective function, right? Those things at a high level. But how? They're not part of that, right? So what we are, okay, so whenever it comes a blue square, that means that it's something that we are trying to do to tackle this, right? It doesn't mean, again, that is the only solution or even a good solution. It's just what we're trying at the moment to try to figure this out, because we have users that are really wanting to understand the model, right? So what we're doing right now, extremely, how you call it, pedestrian. We have a document, usually LaTeX document or some kind of document with formulas that is linked to the model. So we just have in the sync model, we have a comment saying this is this constraint and this is in the model. And we have a mathematical formula of that. Of course, the CP advantage is that our models are very high level. So it's not that far, right? It's for someone, for a fluid domain expert, that will be relatively simple, but it's not ideal. So what we're doing is exploring domain-specific languages. And what do I mean by this? So we're exploring a simpler, restrictive form of modeling language, something that is even simpler than minisync, simpler than ample, simpler than any of these things for that particular domain. That, for example, if you're doing a facility allocation, talks about facilities, about locations, about products, about demand, about things that are for that person. And we have a requirements model in which the user, together with the modeler, formalize that, right? So my work might not work, but at least we're trying that. Now, everything that appears in red means more is needed. More is needed. And here, more is needed to integrate users of modeling. We don't know how to do this, but it definitely is something that we need to do more, because our systems right now are quite removed from the domain experts and they don't understand the model and therefore they don't trust it. Correctness. There was three things. Remember, it was understanding the model and being confident in the correctness of the model. So confident correctness. This is particularly the case for problems in which there is not a clear solution. You cannot just test it against a set of known solutions. And for this particular thing, you know, classic software engineering issue. This is not something that is particularly just for us. So, and it's not just for the domain expert, it's for us, is to know that it actually, the model is correct. It's extremely hard to do. Why? Because our problems tend to be quite complex. And because there tend to be quite a lot of different solutions. So how to know that the one that you have is actually correct and optimal. So something like this. This is a plan layout. Every single piece of equipment, that, well, different colors are different kind of equipment, and also different modules. So that is, you know, a FinFan, that would be a, is it a domain specific? Seeing an example of an instance description with domain specific language would be useful. I haven't prepared any of that, but I'll try to show it afterwards. It would be in minisync mostly. So each of these. Sorry,
Mikkel knows minisync.
Mikkel knows minisync. There you go. So it would be something in minisync. So this is a rack, and each of those things is an equipment. You have your compressors, you have your liquefiers, you have your FinFans, you have your pipes. You have pumps, you have heat exchangers. Well, how do you know that that is correct? We have no way of knowing it. Well, this one, is the same plan? Is a different solution? Is this correct too? And is it better? Is it worse? So confidence, not so easy to figure it out. Certified compiler and solving helps, because it knows that at least if the model is correct and you have a compiler that is known to be correct and a solver is known to be correct, at least you have it. But we don't have certified modeling. So how do we know that the modeling doesn't have any bugs or any misconceptions? It doesn't even need to be bugs. So blue things that we have tried, we have gone the NASA way, which is have several models and make sure that they agree. The CP advantage here is that modeling takes much less time than you think, right? And you only need to actually have one that is fast, right? Which is the one that you're going to give to the company. But still not ideal, because the two of them can agree and still be incorrect. It's difficult when you have, you know, large numbers of things, but and they are done by two different people on different kind of technologies. You want to have a look at the and things that we have not done, well, that you need to, we need to do much better than this. I mean, having 2 models is fine, but improving how to explain explainability of the models and proving correctness of the models is something that needs to have more research in this. So I said confidence and correctness, but also quality. You know, we're going to need sometimes, even us who are complete, we use a lot of, and by that I mean constraint programming, even in areas like SAT, constraint programming and MIP, where we look for optimality, there's sometimes in which we cannot go to optimality because we need a timeout, and because we need to use approximations. And we'll figure out a little bit, I'll talk a little bit about this later. So sometimes we will want to stop early, and then we need to figure out how far from the optimal are we, or rather, the industry asked me, how good is this solution? Is this, you know, is this rubbish? Is this quite good? Is this very, very good? Now, it takes them time to get the concept of a lower bound for when you're trying to minimize, or upper bound, one of the things. But once they do, they want it all the time. They want to know what the lower bound is. And, you know, how good is this plan layout? I can tell them that is, you know, is it optimal, or is it 5.5, 0.7, 2.5? And the lower bound says, and then of course that is from the at most 2.5 from the optimal, right? It might actually be optimal, I don't know, but at most, and that is a great thing to tell industry. So for now, what we do, we use a hell of a lot of Groby mainly, but MIP solvers, because they can give us the lower bound. CP is here in main disadvantage, and anything like evolutionary algorithms, anything that does not provide tight lower bounds is in trouble. So that needs more research there. So that's trust, right? In trust, I've talked about feeling like we have a trust in the model, feeling like the is correct, and quality, knowing the quality of the solution. That was the first of the 4. Second is usability. Okay, so usability. This is obviously key for any decision system, for the adoption. And when I talk about system, I talk about the model, I talk about the solver, and I talk very importantly about the user interface, right? Which is going to be the usability. Classical thing in software engineering again, and I think from my experience with industry that every single optimization system needs to provide significant integration for the domain users, because they're going to want to explore what if this, what if that. Solution diversity, and we'll talk speed and conflict resolution. In addition, you know, we're going to need many more things that are going to need to handle: uncertainty, fairness, online decisions, predict and optimize. But I'm only going to talk about the first 4 because I don't have time for the other ones, and because actually there's not so many work that I've done that takes all the other ones into account, because we still need to solve the first ones better. Okay, so as I said there, interaction, diversity, speed and resolution. Interactions. So the aim often is to explore, right? So they need to be able to interact with the user interface. So a user interface that allows the domain expert to input the data in a familiar format, and I cannot tell you how important this is, because if they don't do things in the way that they used to do it, you might want to change it later to something better, but initially familiar format. And then visually explore a given solution. And by that, I mean things like this. This is a solution for a plan layout. And what we allow them to do is just, they can rotate it, they can move up, down, they can click on the things, they can move things, they can put constraints, eliminate constraints, change the data. First, just view, turn around things and look at it from different places. And also with actual, so not just the plan itself, but also the pipes, costs, and these details of different things, right? And interact with it. So explore a given solution, modify it. So in this particular case, this is one of the components, a big vessel, and every single box there is things that can be modified. They can modify everything, right? And then they say, okay, and apply and run again. And ta-da, we run again. So modify a solution and compare solutions. Wow, this is so needed and so badly done. This is really not done very well. This is an example of how, which is not even, I mean, this is not really comparing. This is just comparing the little data. In here, it takes basically, you're trying to, among other things, you're trying to minimize footprint, right? So you're telling this is a solution that they did by hand. This is a solution done by a system. That means that there's less footprint for that module. This is the 5 different modules of the plan. Better on that one, better on that one, better on that one, worse on that one, worse on that one. But in total, better, right? So you can see a little bit how things go better. This is so pedestrian. And we have, of course, now progressed from that, and we have many others and things like that. But still, it's so this is a different one for hydrogen. So we have basically where to put plants, hydrogen production plants, and who supplies who, right? So each of there's 2 periods in which the demand is constant. So perhaps the first period is 2 years and the second one is 10 years or whatever it is, right? It's a number of years. And this is the decisions that where to build in the first period and where to build in the second period. So that is a plant on a particular location. That's another location, right? So all those things are location. And each row is a solution. So that's telling you that in this particular solution, which happens to be optimal, I built in those 4 locations. And then in the second period, I built those 2 extra, right? I keep the first ones and then I keep more. And it's also telling me who is supplied in terms of north and south. And that is a different solution. And that's a different solution. Each row is a different solution. So this one is very clear to tell you, for example, you immediately saw that plant, that location is in every single diverse optimal solution that we have. And then the domain expert went and said, okay, now give me a solution that doesn't have this plant on, right? You can no longer build there. It was 20% more expensive. So things like that, right? Or comparing things. So not easy. How do we do it? We work with visualization experts because we know nothing about how to compare things properly. So they are the ones who have built proper comparisons and visualizations. But again, lots of things are needed here. In particular, I was saying that, of course, generic, and that's an important way. We don't want to reinvent the wheel. There's a lot of solutions that are kind of similar in particularly for particular domains like allocation of resources, things like that. So generic ways of visualize and compare solutions would be awesome, that people can just grab from some place, and they can. And remember, these comparisons can be for any optimization technology. It doesn't matter whether you have a genetic algorithm, a CP, a MIPA, whatever. You can always use it. So that will be awesome. And also for the interaction, incremental compilers and solvers, right? Or implement an algorithms, in some sense, things that you can add a constraint, take a constraint off, add another constraint without having to recompile and do things like that would be fantastic. So we need more work there. Solution diversity. And this is something that has been really annoying, that a lot of the companies that I work with talk about the optimal solution, and they are convinced that there is a single optimal solution. And it takes a very long time to convince them that, and usually it is by showing 2, but then they go, they cannot be both optimal. And you go, yes, they are. And then they go, no, that's better. And then you start having problem. But showing K maximal diverse solutions is a big eye opener. And if they believe you that they are all optimal, very welcome one. Even better, if you can show them, as I'll show you in a minute, how far from the optimal they are, even better. And it's a very good way to explore diversity measures. So for example, in this one, the diversity measure was that it needed to be at least 1 different from the location. So if you put all the locations you have built as true and false as the ones 0 and 1s, the ones that not, the distance of at least 1 with the other solutions, right? So, and this one, as you can see, the first solution is optimal. The other ones are 0.008 or 9 of difference, which is nothing, right? For them, it's like it's optimal. So that just by seeing this, it immediately go, oh, okay. So, and then they start a different conversation and talking about different diversity. Okay, so things that we have done. Well, we have integrated a basic version of what Ingmar et al. Did presented in III 20 into Minisync, which hopefully will be in the next Minisync release, which will be awesome because then it's generic. Any model can use it. That will be fantastic. But we need to do many more research on this. And one of the main issues for us, and thank you, yes, we think is incredibly interested, and we will love to have more people doing research on this, is speed. Speed is a massive issue because, for example, the basic version of INGMA is you first go optimal, and then from there on you change the optimization function to be, now it needs to be with, and then you put a constraint that the next one needs to be either optimal to or within this of optimality. You want them maximally far away according to that diversity measure. And then the next one is maximal far away from the other two, and then maximal far away from the other, which becomes more and more difficult and more time consuming. So if you have something that speed is a major issue, because diversity needs something that is in the order of seconds or hours, less than 1 hour. And if you can do it in a matter of like minutes, even better. Now, speed is also interesting because most users want flexibility. They want to be able to go to get a coffee, and when they come back, get something that is roughly correct, roughly optimal, but doesn't need to be totally optimal. But if I go tonight at home, I want to run it with the exact solution, which means that you're going to need, so what are we doing for this? We're doing approximations, lots and lots of approximations, and approximations of the data, approximation of the model, and approximation of the search. Now, and this is the interesting part, each of them, they need to be carefully selected to try to affect the decisions, the high-level decisions at the minimum. For example, in the hydrogen plant allocation, the main decisions is where am I going to put my plant, how big is it going to be, and who is it going to supply, right? Then, of course, the electricity consumption, when exactly, and all the details are also important, but they do not affect in general as much the big decision that is where do I put my plant and how big to make it. So I can abstract, if I want to go faster, I can abstract the details of the pricing of the electricity by hours. The input data is given by per hour for an entire year prices. I can approximate that by days, by tiers, by seasons, by a lot of things without affecting much the solution. Same with the model. I can relax the model by, either simpler or less constraint. I can remove constraints that only affect the operational daily consumption, not the big decisions. And the search, that's classical. We now all the time do approximations of either the data or the model or both. And then once you get the approximate, you feed it up back into a warm start for MIP. And then we use large neighborhood searches. And that's the kind of thing that we do. But many more things can be done. And we also compare approximate and accurate solutions, which is a great way of finding most influential parts. So if we have, you can compare the optimal value. But the optimal value usually is not the solution, the decision. The decision is where do I put my plant and how and who supplies who. So for things that may have 10% increased cost, but they have the same decisions, they agree 100%, which actually happened for us when we were modeling correctly, as in modeling well for that particular kind of approximation, we ended up having the same high-level decisions, even though the objective value was much worse, because it was not being able to choose the best price in that day or this other day, but it didn't matter, right? So it's a really good way of and I think that is an interesting thing to do too. And what we do is use Gurobi most of the time. No CP solvers, not SAT solvers, mostly Gurobi, because it's often the faster. Well, it could be seedless, it could be or our tools too, but it's often the faster. It has warm starts, effective warm starts, and it handles floats. And I cannot tell you how important floats are. And that is in the red box. So the things that need to happen better for CP in particular, but for other methods too, is there needs to have proper, effective warm starts, right? You need to be starting from something that might or might not be a solution, but is in the area of that things that you want to do, and actually being useful in cutting the search to get quickly to an exact solution. Very, very important. And we also need generic approximations. It would be fantastic if we can recommend not only things like symmetry and redundant constraints and kind of modeling, but also approximations for particular things, particular domains, perhaps, particular global constraints, classes of problems. Okay, conflict resolution was the other thing that I mentioned. As soon as you allow domain users to start interacting with a user interface, you're going to be in trouble. Because the system is going to say no, as in invisible. And even Google does it. If I tell Google that I want to go from Melbourne to Madrid by car, it tells me this little thing there. So to Melbourne to Madrid, it tells me, sorry, we could not calculate the driving directions from Clayton to Madrid. Now, two things there. Yes, that's true. We cannot calculate the driving conditions, but it doesn't tell me why. The first thing is there's no road connecting the things. And it doesn't tell me how to fix it, which is use the bloody plane, which I have there. So it could tell me, use the plane. I can't find you one by plane, but it doesn't. So it doesn't explain what the problem is, no roads, and it doesn't tell me how to solve it. And that's things that we want from Google, but also from any system. So what we have done is to integrate the sensorial constraints article into Minisync, which allows for all these things. So what is the main idea is to, when things go right, wonderful. But when they go wrong, we want to give information that tells that this is the reason, and this is ways of fixing it. And then you give that, and the user will figure out how to fix it, and with a bit of luck, we'll get back to a solution. So how do we do that? And we want to do it in generic ways and do it flexible. So the first part is the traditional. You have a problem, you give it the data, get an instance, you flatten it, you solve. Fantastic, you get a solution back. Fantastic, that's good. But if there is no solution, we want to be able to sometimes be fast, but usually when things go wrong, it's like a bug in a program. You can have lots of different bugs disconnected, more than one, or you can have bugs that are intersecting. You fix one and suddenly all of them are fixed, right? Well, it's the same. You might have one single bug, or you might actually have a lot of them, and you might want to figure out, the system might be able to give you all the choice. And you said, I want to fix this one, and then tell me again and see whether there is still an issue. And yeah, we tried things that are just faster. And once we provide this with the choice to the user, we want to help them to repair, right? To tell them by softening the constraints. So the constraints that said, this set of constraints, the one that I want to fix, we can soften it by adding slack variables, so whatever is the method, and then you solve it and you tell them, well, this is the error margin that you get, and if you modify this, it will be healthy. Okay, so for example, this is different generic visualization. We have a textual, so this is for plan layout again, that the problem, there's 3 different constraints that are a problem. One of them is the minimal distance between this and that. You can also have it in terms of graphs. This is more interesting because all these dots are constraints that are in bags. In this, what we call a minimal unsatisfiable set of constraints that altogether just not inconsistent. And these are the masses. Minimal unsatisfiable test. For example, this mass contains all those constraints. This mass contains all those constraints, and that one plus that one plus that one. So everything that is connected through that tells you the kind of constraint that he's talking about. So the colors is the kind of constraint of those constraints. Those are the masses, so the minimal unsatisfiable sets, and those are the equipment that is involved in those constraints, you know, minimal distance between assembly 0, assembly 1, etc. So what the user can do is, as soon as it clicks that, it immediately tells it that 1, 2, 3, 4, 5 masses, that one and those ones, they're all solved, right? If I fix that, if I fix as in, if I improve that, if I change that in a good way, it will, but still that mass is not fixed, is not resolved, because I need to change something there. So it needs to immediately, you know, decide which of these ones wants to change. Do you want a group side, or you prefer to change minimal distance? And they can figure out, etc. And completely generic, that can be work, and we are using it now for everything. And then you also have a network in here. Every square is an equipment, and the kind of constraints are represented by squares. That basically saying that there is a group size of those group of equipment, or it might be that is the minimum distance between those 2 equipment, etc. So putting it all together, you provide with a good interface, good visualization, then you report inconsistencies. Then once the user has selected, you give it the slack value of how things should change, which in our case, it would have been go by plane. And then they fix it, and hopefully they get to a thing. So yeah, there are different things. So this is the things that we are doing. What it can be done. Lots of things. Most research, still too many masses. I've showed you an example with 6. In reality, there could be thousands upon thousands. And why? Often because, for example, in plant layout, imagine that you have an equipment that you have moved, you wanted, and what if I move this here? And suddenly it conflicts with everything around it, right? So it's too close to this one, too close to this one, too close to this one, too close to this one. Every one of those is a mass. So you end up with, as many equipment you have close to that. So we need to find patterns that rather than giving you every single one, it tells you this is too close to anything within this amount of meters. That would be much more useful and much more meaningful. We also need generating softening and constraints. We know how to soften linear constraints very well, and we know how to soften logical constraints that are simple logic constraints. We don't know how to soften some global constraints like circuits or sub-patterns or homo, lots of all the things. And also it would be great to explore user preferences on how to do this, which we don't do right now. As I said, all the things that we can think about it, but we're not having time. So we were just looking at the interactability, the diversity, the optimality, and the conflict resolution. Practicing. That's another of the 4 that I mentioned. None of my skill set. I know nothing about this. I'm interested in the brains, not. So what are we doing right now? Recommending the company to engage a software company like Combinatorial, or engaging the company's software department. Is not in our skill set, but we need to make this from the beginning, because that has caused us a few issues when they think that we're going to do the final product. And I don't know you, but I'm not a software engineer of that product level of the testing, and I don't want to do any maintenance and that kind of thing. So this needs to be reminded of often, because there's an extra cost, and they're quite expensive. So, and I bet that a lot of issues of good systems not being deployed is because of this. So, but careful that if this is happening, it means that the partner is not the main user. They're going to commercialize it. They're going to want to commercialize it, and also means that sometimes they're not as interested as if they are the main user. Okay, that's all I have to say about products. It's not my thing. Maintainability, and this I'm interested very, and this is of course something that is very well studied in software engineering, right? This is a very classic thing. And the question is there anything specific here for us? Is this particularly? Well, I think it is. And I found it interesting because I think that we're in a better position than many other software systems. Why? Because of a higher level. So it's very common to change the user requirements in any software system. But for us, they might be such that if we do a good job in other parts, it is recoverable. So we have what we call program drift, right? You have slight changes of input parameters, slight changes of constraints, slight changes of objective function. And we're trying, what I talked about before, the domain-specific languages. You remember this picture that I showed at the beginning? That we can have a requirements model in this kind of simple language. Well, if we are clever enough to not only have these arrows, but also have these ones in which the requirements model can compile directly to a mini-zing model or to a whatever model it is. And we let the user, the domain expert, modify some things, but not all. So perhaps they cannot modify the variables because they are super important for this, the correctness and the model. But other things like, they might be able to add new parameters, new constraints that are based on the old one, modify the objective, the weights or something like that. I think that we can do things there. However, there's so many things that are not done. Well, we don't even know whether the domain-specific language for modeling are good or not. They might not work at all. So we need to evaluate the effectiveness and the overhead. But there's many other things that can be done. And particularly, we think that work on templates, right? Templates for optimization problems in particular areas, like a class that you start with allocation, fund allocate, resource allocation, which there's or rostering, and then that gets done into node rostering and company rostering and the other kind of, and then that gets done into. I think that could be something good. Or reusable model components, like in the library kind of inspired. So we need to go more towards these things in order to make it easier. And generic user interfaces components, like I was talking before, visualization, comparison, etc. Okay, so that's pretty much it, which just in summary, just focusing on what I think that needs more research on, integrating domain in terms of trust, integrating domain experts in modeling process, demonstrating modeling correctness versus the requirements, and generating title level bounds to show quality. Usability, incremental compiler solvers will be awesome for being able to what if scenarios, generic ways to visualize and compare solutions to make life easier to the modelers, warm start methods that are effective, aside from MIPS, MIPS solvers who have them. Automatic generic approximations, the more the better, to generate speed and be flexible. Widespread handling of floats, please. Constraint programming, get your act together and use floats. Need more research on what else. Softening of constraints, generic softening constraints for complex constraints, meaningful patterns for constraints like masses. So better explainability, user preferences for constraint resolution, and then maintenance. User modifiable requirements model, so something that the user can modify and generate the new model. Templates and reusable components to make it more kind of class or library oriented, and a generic user interface components. And that's it. That's and I'm on time. Yoo-hoo!